Okay, evaluate the line integral, blah, where C is the boundary of the annular region in the first quadrant, bounded by the circles. Okay, so we have circle radius 1 and circle of radius 3. Oh, I see. Okay, so we could parameterize this. Um, or we could do Green's theorem. And Green's theorem looks like it's going to be a lot easier, right? Because this looks like it'd be a lot easier to integrate over this whole region than having to integrate over each of these portions. So using Green's theorem, we have the integral of, I'm just going to write it this way because this way makes it a lot easier to see what's happening. Okay, so this is my f. Now, real quick, I can check if this is conservative. If it's conservative, if it's a conservative vector field, I'm done and the whole thing is 0. So let me at least check that real quick. So if I do the partial, so this is f, of the x component with respect to y, what do I get? I get minus x squared. And if I do the partial of the y component with respect to x, I get y squared. I get y squared. So it's not conservative vector field. They're not the same. That's fine though as far as we're wanting. It just means that it's not 0. Okay. So what I can do though is I can use Green's theorem that says that integral around a closed loop of f dot dr, right? That's what this is. This is my dr basically. Is equal to the integral over the enclosed domain, right? This is the domain of this right here. Minus is that right? Or did I do it? No, that's right. Um, I did the minus signs backwards. It's fy dx and then fx dy. Fy dx minus fx dy dA. Okay, so I'm just doing the difference of these two. Okay, and doing this right now, I'm integrating over this region. And this region is actually going to be really easy to integrate over when I convert it to polar coordinates, right? Because I have theta and r is clearly going from 1 to 3. So let's go ahead and convert this. So this is what I wrote this up here. This is y squared minus x squared. That's plus x squared dA. So if I write this in polar coordinates, this becomes the integral. So r is going from 1 to 3, right, because it tells us that in the question, right, bounded by the quadrant of the quarter circles from x squared plus y squared equals 1 and x squared plus y squared equals 9. So that means that r goes from 1 out to 3. And then theta is just going to go from 0 to pi over 2. X squared plus y squared equals r squared. And then I'm integrating with respect to polar coordinates, so I have r dr, nope, d theta dr. Okay, this is separable, so I get integral from 1 to 3, r cubed dr, integral from 0 pi over 2 d theta gives me r to the 4 from 1 to 3 times pi over 2. That's 81 over 4 minus 1 over 4 times pi over 2, which is 80 over 4, which is 20, so this comes out to pi over 10. Right, yeah, so that's 81, 81 over 4 minus that, so that's 80 over 4, which is 20, 20 over 2, which is 10. Okay, so I get pi over 10, which is not correct. It says 10 pi. You're right. You're right. I totally did those fractions backwards. Yeah, so I have 80 divided by 8, which is clearly 10, and I can't do preschool math. Thank you very much. Next one. So real quick, that's the whole point of Green's theorem, is that it lets us take a line integral around the boundary and turn it into an area integral, which is generally easier to compute. Sometimes it's useful to do it the other way too. Use Green's theorem to find the area enclosed by the asteroid, blah. Okay, so it tells us how to parameterize it. Right, so we have r of t equals a cosine cubed t, a sine cubed t. What does that even look like? I don't know. I'm just curious. So I'm gonna type this into the chat real quick. Y to the 2/3 equals a to the 2/3. Let's just set a equals to 1. Okay. So we want the area. So what we're actually interested in, we're interested in this, and we want df y dx minus df x dy. We want this to be 1. Okay, so let's see, what do I want to do? If I pick fy equals x, that's going to be 1. Let's put 2x. And we do x. And then I do fx is equal to negative y. Yeah, so if I pick this, right, so then this becomes 1. This is also going to be 1, so it's going to be 2. So this is going to, so the area, no, I should do this over 2. There we go. So then this becomes 1, and then I can change this into a line integral. and I don't have to worry about what are the bounds on the x and y coordinates. Okay, and how did I pick this? I just picked really any function that would satisfy this. Okay, so now I can change this into, this is equal to the integral around this curve of fx x over 2 dot dr. So now I need to put everything in terms of r. So this is the same as the integral from, so t goes from what? 0 to 2 pi? I'm going to assume that t goes from 0 to 2 pi. Okay, so we have this minus y over 2, x over 2 times r prime, sorry. So what is r prime? 3a, I need more room for that. R prime of t is 3a cosine squared t times derivative of cosine is negative sine, comma, that's going to be 3a sine squared t derivative of sine is cosine t. Okay, so that's my r prime. And then if I put this in terms of r, I should put this in terms of, you know what, let me factor out the 1/2. Okay, and then I have negative y, which is negative a sine cubed t, and then x, which is a cosine cubed t, dot minus 3a cosine squared t sine t, 3a sine squared t cosine squared t. I hope a lot of stuff cancels out. Okay, so that's 1/2 integral 0 to 2 pi. We do the dot product. That's going to be positive 3a squared. Hold up. Yeah, that's right. Yeah. 3a squared, sine to the 4th cosine squared, plus 3a squared, let's see, that's sine squared cosine to the 4th t dt. Okay, so I can factor out 3a squared over 2. And then I have integral 0 to 2 pi sine to the 4th cosine squared t plus sine squared t cosine to the 4th t. Okay, so you know what, I can factor, that's going to simplify quite a bit. I can factor out sine squared cosine squared from each of these. So I have sine squared t cosine squared t. I can factor that out, and what I'm left with is sine squared t plus cosine squared t dt. That's 1. So I'm left with 3a squared over 2 integral from 0 to 2 pi sine of what? If this was 4, that becomes 8. And you'll see why I did that. So I multiply and divide by 4. I have sine squared t cosine squared t dt. Then to make life easy, this integral becomes 3a squared over 8 integral from 0 to 2 pi of sine of 2t squared dt. And then I can integrate this, and I get 3a squared over 8. So I'm integrating 1 minus cosine of 4t over 2 from 0 to 2 pi dt. Bring that 2 out in front, 3a squared over 16. So I integrate these, and I get t minus integral of cosine is sine, 4t over 4 from 0 to 2 pi. Okay, so I have 2 pi, and then the sine terms both cancel out, and then 0 obviously also cancels out, which gives me 3a squared times 2 pi over 16. Those cancel, and I get 3 pi a squared over 8. That I expect would be too long for the test, but I don't actually know that for sure. Yeah, that's correct. One second, let me double check that that's correct. 3/8 pi a squared. 3/8 pi. Okay, what was your question? Sorry. Okay, you keep cutting out. Can you type the question in the chat? Okay, yeah, so I had sine squared t cosine squared t. Okay, so I had sine squared t cosine squared t, and this was 1. Um, so I wanted to be able to put this in terms of sine of 2t. So all I did was I multiplied this by 4 and divided by 4. So this would have been a 2, but when I multiply and divide by 4, I get 8. And that way, this becomes 2 sine t cosine t squared. 2 sine t cosine t is sine of 2t. So that's why I thought ahead to go ahead and multiply by 4. So you probably would have done this maybe a slightly different way. You could have done that sine, how would you do that? You could have said that sine times cosine is sine of 2t divided by 2, and then you would have squared that and had the 1 over 4 on the bottom. So you would have gotten the same thing. I just happened to multiply and divide by 4 to do it. Okay, next question. Calculate h.dr where h is the vector field. Actually, real quick. So here we have the line segment, so I need to parameterize the line segment. So I know that if I do p times 1 minus t plus q times t, right, where this is p and this is q, this is going to parameterize the line for me. So this is going to be r of t. So I have 1, 1 times 1 minus t plus, or I guess I should do this row vector, plus 3 minus 1 times t. So this is 1 minus t, 1 minus t, 3t minus t. I add them together and I get 2t plus 1 and minus 2t plus 1. Yes. Okay, and when I do it this way, I know that 0 is going to be less than or equal to t, less than or equal to 1. Because at 0, I get p, and at 1, I get q. So from 0 to 1 gives me this line segment. Okay, so I want to integrate. Also I should figure out what is r prime. R prime of t is going to be 2 minus 2. Okay, now I can integrate. Integral from t equals 0 to 1, h, which is x plus 2y, x minus 2y, dot r prime dt. So I need to put x and y in terms of r. So we have that from right here. So we have 0, 1, x plus 2y. So I have 2t plus 1 minus 2 times minus 2t plus 1. So that's x plus 2y. Then I have 2t plus 1 x minus 2t plus 1 minus 2y. So I simplify that, dot 2 minus 2 dt. Okay, so let's start simplifying. So I have integral from 0 to 1. Here I have 4t, that's going to be 6t, minus 2 plus 1, it's minus 1. And then I have 6t again, plus 1, minus 1. Did I lose a 2? That's supposed to be minus 2y. Okay, so that's going to be plus 1, minus 2, so it's going to be minus 1, dot 2, minus 2. And then I do the dot product, and I get, since these are the same thing, wait, this is just going to be 0. Right, because I have 2 times this plus negative 2 times the same thing. Is that right? Did I make a mistake? This is number 5. Nope, that's correct. Okay. Now we integrate this, and it gives us r of u. First thing I should do is compute r prime. That's going to be e to the u minus e to the minus u and 2e to the 2u. It gives us the bounds on u, and I should also write h in terms of u. So x times z, that's going to be 2 e to the u, e to the 2u, y plus z, That's going to be 2e to the 2u. No. This is not right. That 2 shouldn't be there either, right? Because this is x, y, and z. So x times z is this, okay? And then I have y plus z. That's e to the minus u plus e to the 2u. And then this is just x, which is e to the u. This will simplify e to the 3u. That doesn't simplify. Okay, so I have integral from 0 to ln of 2, because it tells me here. And then I have h dot r prime dt equals integral from 0 to ln of 2. That's e to the 3u e to the u plus, or minus e to the minus u, times e to the minus u plus e to the 2u plus 2 e to the u e to the 2u du. That should be du, not dt. Okay, start simplifying, and I have integral 0 to ln of 2 e to the 4u, and I'll distribute, so I have minus e to the minus 2u minus e to the u. This is plus 2 e to the 3u du. Okay, let's see. So I can integrate these, and I get e to the 4u over 4. This is going to be plus e to the minus 2u over 2, minus e to the u plus 2e to the 3u over 3 from 0 to ln of 2. Okay, so I plug ln of 2 in, and what do I get? I end up with 2 to the 4 over 4 plus 2 to the negative 2 over 2 minus 2 plus 2 times 2 cubed over 3 minus, when I plug in 0 to each of them, I get 1 on top. So I have 1 over 4 plus 1 over 2 minus 1 plus 1 over 3. This looks really gross. Is that anywhere close? Oh, it's this one. Okay. Yeah, that looks half right. Okay, so this is going to be 2, 4, 8, 16 over 4 plus 1 over 8 minus 2. That's 8. That's 16 over 3 minus 1 over 4 plus 1 over 2 minus 1 plus 1 over 3. Okay, I'm going to go ahead and add the corresponding fractions. So I have 15 over 4. That's going to be 4 over 8. So I have plus 5 over 8 minus 3 plus 1, 7 over 3. Okay, so the common denominator, that's going to be 24. So first one needs to multiply by 6. 15 times 6 is 90. Yeah. that needs to multiply by 4, that's 20. That needs to multiply by 24. 3 times 24 is 72. This needs to multiply by 8 times 17, which is what? 136. All over 24. Okay, so what I get, I have 110 plus 136 minus 72 over 124. Looks like some of my fractions might have, oh sorry, not 124, just over 24. That's 246 minus 72 over 24. That's what? That's 174 over 24. Okay, so that's not quite right. Or that's not the same as the answer. Did anybody work this one out and actually get the right answer? Because I bet my mistake is somewhere in these details. So that's 2 to the 4. Actually, let's make sure. So I have so derivative, that's the same. Shouldn't the 1/3 at the very end be a 2/3 here? It should. Man. Thank you. I bet that's it. So when these get added, that's 18. Hold up though, that doesn't quite fix my problem because now I have 8 times 18 which is 144. It's still going to be an even number, so that's still not quite right. So that's 144. That actually makes it even more off. Does it? I don't know. 144. That's 254 minus 72 is going to be what? 182. Yeah, that's even more off. But that was a valid mistake. So let's see. So we have r prime. So that's e to the u negative. That's the 2. Okay. We have h. That's going to be okay. E to the minus u and e to the 2u. Okay. And z is e to the, or x is e to the u. Okay. And we do the dot product of these two. So this times this, that's 4. Okay. I distribute, so we get negative 2u, okay, and negative e to the u, okay, and e to the 3u. That looks good. Okay, so then plug ln of 2 in, so I get 2 to the 4 minus 2. Okay, so this is going to be 2 everywhere. All right, I plug 0 in. I get 1, 1, minus 1, and 2/3. Okay, so I bet my problem's in the fractions here. So this is 16. This is going to be, this has to be 1 over 8, yes, because that's still a 2. minus 2, and this is going to be 8. I have minus 1/4. This. There it is. I found it. Negative, negative, that's positive. So the signs on a lot of these are wrong. Okay, so I have 16 minus 1/4, so that's 15 over 4. Here I have 1/8 minus 4/8. That's going to be minus 3/8. Minus 2 plus 1, that's minus 1. 16 over 3 minus 2/3, that's plus 14 over 3. There we go. Okay, and let's finish erasing all this. I bet this does it. Okay, so common denominator again, I said was 24, that still holds. So this needs to multiply by 6. Again, that's 90. Minus, that needs to multiply by 3, so that's minus 9. Minus 24 plus 14 times 8. Which is 112. Over 24. I don't know if this quite does it. I'll have to check these again. Okay, so this is 202 minus 31 over 24. I'm so close. Because this is now 171 over 24. How is that 2/24 off? Okay, so something's wrong with my fractions. Again. One more check and then I'm going to move on and just blame it on fractions. Okay, so we have e to the, we have 2 to the 4 over 4, okay. 1/2 squared, no, yeah, 1/2 squared over 2. We have minus 2 plus 2 cubed. 2 cubed over 3. Okay, we plug in 0, we get 1/4 plus this minus this plus this. Okay, that's 16. That's going to be 1 over 8. That's minus 2. That's 8 times, okay. And this is all still good, 4 over this. So we have 16 over 4 minus 1/4. We have 1/8 minus 4/8, that's minus 3/8. Minus 2 plus 1, that's minus 1. And this. Okay. 15 times 6 is 90. Minus 3 times, so we need to, 3 is 9, 24. We multiply that by 8. Okay, so I'm not sure what's going on with this. I'm going to say this is my answer, even though the answer given was 169 over 24. Okay, but I think that's close enough that we see that the problem is somewhere, probably somewhere here in the fractions. Or maybe that answer is just wrong and mine is correct. I hope that's the case. I'll check it later. Also, if you guys want to work that out and see what you get and confirm that I'm right, that'd be awesome. Okay, determine whether the given vector function is the gradient of a function. If it is, find all such functions. Okay, so here all we do is we do the derivative of the x component with respect to y. So that's going to be 3x squared times 2y. It's going to be 6 plus 3. And then we do the derivative of the y component with respect to x. That's going to be 6x squared y plus 3y, like this. These are not the same, so not a gradient. We say it's not a conservative field. Okay, moving on to the next one. I do the same thing. Derivative of the x component with respect to y, and I get, this stays the same, e to the y, and those go away because they don't depend on y. Then I do the same thing for the y component, derivative with respect to x, and I get, that's going to be x e to the y, 2x e to the y, that's 0, and that's 0. So these are the same, so that means that yes, this is a conservative vector field, and I can write it as the gradient of some function. So if I set f(x) equals df dx, right, that means that I'm setting 2fx equal to 2x e to the y plus e to the 2x minus 3, and I integrate both sides with respect to x. I get x squared e to the y plus e squared x over 2 minus 3x plus stuff that involves only y plus a constant. And now I do the same thing for the for the y component. I integrate it with respect to y. So I'm integrating x squared e to the y plus cosine of 2y plus 1 dy, which is equal to, so this doesn't change, I have x squared e to the y, integral of cosine is sine, plus y, plus stuff that involves x plus a constant. Okay, so now I go through and I look at what's the same. The terms that are the same, right, that's going to be this one and this one, I only put once. So f equals x squared e to the y. Then I look at what is my stuff that involves only x. It's going to be the terms up here that involve only x. So I have plus e to the 2x over 2 minus 3x. And then I look at what is the stuff that involves only y, and it's going to be down here. Plus sine of 2y over 2 plus y plus some constant. And that's my potential function.